So, good afternoon, ladies and gentlemen. I think it's time now to start the session. As you know, it's already the second session on very high cyclic fatigue, but it will be a very, very short session because we have just one contribution. My name is Hans-Jürgen Christ, I'm coming from the University of Siegen, and it's my pleasure, of course, to chair the session. And as you know, it will be a very brief job today. The only talk we have will be presented by Anthony Grigorescu, who is also coming from the University of Siegen. And he will present some results of one of the projects of our priority program, SPP 1466 we call it, and the title, well, you can read the title of the introduce.
Thank you. Thank you very much, Professor Chris, for the introduction. Ladies and gentlemen, good evening and welcome to my session and series. I will speak today about the effect of martensite contact and geometry of the inclusions on the vhcf behavior of predeformed metastable authentic stainless steel. As Professor Chris said, this is part of a larger project which is financially supported by DFG in Germany. I will give first a short introduction of this topic, and then I will present the materials and the testing procedure. In the main part of the presentation, I will present the results of the fatigue test, about the damage mechanism and noise sensitivity, and I will conclude my presentation at the end. So, the metastable authentic stainless steels are very widespread for the use in the metal sheet forming industry. So it is of great importance to know the fatigue properties for the predeformed conditions of this material. The low cycle and the high cycle fatigue properties are very well known due to extended investigations in the last decades, but the very high cycle fatigue properties are a relatively new topic for the predeformed condition of the material and represent the aim of this presentation today. The steel that I used is the IC304L, which is a metastable authentic stainless steel. As said, it lies in form of metal sheet with a thickness of 2 millimeters. The material contains a high number of oxydic inclusions, and these inclusions have a special geometry like an elongated ellipsoid. And these elongated ellipsoids are not distributed homogeneously, are not orientated homogeneously, but they have the longer axis parallel to the rolling direction of the metal sheets. This means that if we extract samples parallel to the rolling direction and we look at metallographic sections perpendicular to the applied stress, we can find sections of these inclusions with a circular shape and a small area. On the other hand, if we extract samples perpendicular to the rolling direction, so in the transversal direction, called TD samples, the projected area of such inclusions would have an elliptical form and would have a larger area. These two conditions were systematically investigated, and the results of the fatigue tests will be presented in this presentation. So the only difference between the RT samples and the TD samples is the orientation of the internal inclusion respective to the applied load. In the as-received condition, the recrystallized condition, the material has a fully austenitic microstructure, but during the plastic deformation, some parts of the microstructure can transform to alpha prime martensite, so that we get a quasi-duplex microstructure consisting of different amounts of austenite or martensite. We can regulate the amount of martensite by controlling some parameters of the predeformation, like the deformation degree or the environmental temperature. After that, fatigue samples were machined and tested in the high cycle and very high cycle fatigue region. The three predeformation conditions that I investigated are with 30% martensite, 60% martensite in the rolling direction, and 60% martensite in the transversal direction. We can observe already at 30% martensite that the martensitic needles start to form a network, a coherent network, whereas at 60% martensite, we can find large clusters of martensite in the microstructure. If we take a look at the inclusions present in the material for RT samples, these are sections made perpendicular to the applied stress. It's a high probability that the inclusions are located in the martensite cluster. In this case, it would be something like here or something like here. EBSD measurements show such an example in this micrograph. For the TD samples with a elongated shape, Here's another scale. It's not comparable to this. This inclusion is much larger. It's less probable that the whole inclusion is surrounded by a martensitic phase. This would have a major influence on the damage mechanics of this material, as we shall see in the next slides. I'll come now to the results of the fatigue test. In the as-received condition, we have a true durability without failure up to 10 to 8 cycles. If we increase the martensite content to 30%, we increase also the fatigue strength, and the material still shows true durability. But at much higher martensitic contents, in this case 60%, we see observed internal crack initiation in the vhcf regime, and the fatigue life decreases after 10 to 7 cycles. This is due to a combination between the inclusions and the high notch sensitivity of the martensitic phase that we built during the predeformation. The mechanism of crack initiation and fatigue failure is similar to the high-strength steels, with crack initiation at the inclusion, forming of the FGA, and the typical fisheye morphology of the fracture surface. If we change the applied load direction from the rolling direction to the transversal direction, we observe also a shift of the ascent curve to lower number of cycles, and this is due to the fact that the projected area of the inclusions in the TD sample is larger, having this elliptic shape. Take a closer look at the mechanisms. We see here the fracture surface of the RT sample, and we obtain metallographic sections through the middle of this inclusion, and I show it here. The applied stress is in this direction. This would be here the crack surface. First, it's confirmed that crack initiated from these allocated inclusions, but not as expected in a plane corresponding to the larger section of the inclusion, but somewhere above this plane. And EBSD measurements show that in this region, the inclusion was surrounded by the martensitic phase. So the conditions for crack initiation for RT samples is very dependent on the local microstructure, and we also expect microstructure dependent, so an inhomogeneous FGA formation and growth. For the TD samples, we did the same investigations. In this case, we see that crack initiated the section corresponding to the largest area of the inclusion, and microstructure characterization shows that cracks can also initiate in the austenitic phase but are arrested by the microstructure. The only effective mechanism for crack initiation and fatigue failure is the FGA formation in a plane perpendicular to the applied stress. For this case, we have higher stresses at the inclusion due to larger projected area, so we have a very strong influence of the crack initiating inclusion and less influence of the local microstructure. All these statements, however, have a more or less pronounced assumption character, so that we also applied fracture mechanics theory in order to support these statements. For the RD samples, we calculated stress intensity at inclusion, and we see only a very weak correlation between delta K and number of cycles to failure. Because this is explained by a very strong influence of the local microstructure, especially for very low delta K values beneath 1.8. The area of the FGA is larger for higher number of cycles to failure, which stays into the agreement with the literature, and because the FGA formation takes the highest amount of the fatigue life. For the TD samples, however, the projected area of the inclusions is much larger, as well as the delta K calculated at these inclusions, and we find a very good correlation between delta K and the number of cycles to failure. In this case, the FGA area doesn't correlate very well with the number of cycles to failure, because the scatter of the inclusion has a larger influence on the fatigue life and occupies the larger area of the FGA. So the inhomogeneous distribution of these inclusions is responsible for the large scatter of the fatigue results. We can conclude that, at least for TD samples, the dimension of the inclusion, the applied stress, and the notch sensitivity of the microstructure are the main parameters controlling the fatigue life in the vhcf regime of predeformed metastable austenitic stainless steels. In order to have a quantitative idea about the large sensitivity of the microstructure, I performed tests with a smooth specimen and large specimen with a K value of 3.2. And the fatigue results are present in this graph. And the calculated notch sensitivity showed that already at 30% martensite, the notch sensitivity increased very much, whereas further increase in martensite content doesn't result in even stronger increase of notch sensitivity. I'd like now to conclude my talk. During the predeformation, 30% martensite, the martensite needed to start to form a coherent network. For volume fraction at or above of 30% martensite, the material exhibits true durability without fatigue failure up to 10 cycles, whereas higher martensitic volume fractions, internal crack initiation occurs and the fatigue life decreases in the vhcf regime. A change of the direction of the applied stress from rolling direction to the transversal direction results in a shift of the SN curve to a lower number of cycles. For the TD samples, we could see that the dimension of the inclusion is the main parameter controlling the fatigue life, whereas for RT samples, it's not the same. In this case, the local microstructure in combination with a very low delta K results in a very inhomogeneous FJ growth, so that we cannot correlate the dimension of the inclusion with the fatigue life. The nerve sensitivity test showed that for predeformed austenitic stainless steel, martensitic amount above or lower than 30% should be obtained in order to have optimized HCF and vhcf properties for the deformed martensitic or austenitic stainless steels. Yeah, I'd like to thank you for your attention.